All right, getting things started. Welcome back, everyone. Week 7, which should be the second to last week out of our 8-week and then final total schedule. So congrats again on making it this far in the class. Thanks for sticking with it. I hope you guys are learning and having fun and all that good stuff coming into the class, knowing less than you know coming out of it. Now we're going to take attendance, and then we're going to be doing Arduino today. So more Arduino stuff, as in C and C++ stuff or microcontroller related stuff, kind of everything that's related to the last lab, give you some more context and lecture on that for a while. We'll also be going through a new programming language, the function block diagram, which is a little bit different than ladder logic or ladder diagram and structured text that we've used before, but is similar to ladder logic. So I think you guys will be able to handle it. But we're going to be going through those things, have a little bit of Arduino practice, and then just probably a little bit of time towards the end, like usual, to finish labs if you guys need that opportunity to do so. Okay, any questions before I get started on attendance? Maybe questions on the previous lab? Yeah.
I was just saying this. Is the final on Wednesday of next week? Or is it on? Okay.
It'll be on the 12th. Let me double check. So it's on the syllabus. Should be anyway. So yeah, May 12th. I believe that's the week after next, yeah? Yeah. Because next week is the 7th.
Oh, yeah.
Yeah, so final week and then the final. Final. Okay, good start. Any other questions? All good? Passed? Okay. All right, so as usual, this presentation is in the weekly updates folder. There aren't really as many links in this one, but there are still plenty of good things within the actual context of the presentation. Okay, so more vocabulary, or at least a vocabulary review of what we've gone over before. So, key in if you haven't written some of these definitions down, or if there's anything new to you that you don't quite understand or remember, make a note of it. Do what you can to bolster your memory going forward. All right, so talking a little bit about Arduino, quote unquote, or what people say when they mean the Arduino programming language. Fun fact, it's actually C and C++ in a trench coat, essentially. That we have some special functions to knit it all together, but otherwise it, for all intents and purposes, is C and C++. You can use C, actually, which is kind of like a step above assembly code, directly in Arduino. You can call C functions and C variables, and it'll work just fine. Like literal code will compile within Arduino for C and C++. But we also have special functions in there that make our life easier from a quality of life perspective. Okay, there's, for example, pin mode. The idea of pin mode and what it does, and to configure a port, and like what it means to configure a port. As you might imagine, the actual machine code of it all is more complex than just configuring a pin, right? There's more processes that have to happen. And pin mode, when we call it, handles those processes for us. There's bits that get set places on and off, and in order to coordinate the configuration in order to do certain pins. The way that pins are addressed is a little weird. For example, it's not 0 through 13. There's like 3 or 4 different ports, and then certain pins are on certain ports, and you just kind of have to remember what they are. Except Arduino handles that for us, where it's saying that certain pins are just like, this is pin 12. It's not, port A, pin 0, right? Which would be like digital pin 11. It's just the number 11 pin, and it's easier to use going forward for hobbyists or anyone else that wants to use it. It's a little bit more human, right? Easier to deal with than C or C++, or because remember the microcontroller that's in the middle of all this, and we'll talk more about that in a second, is typically programmed in what's called a native programming language, or a native SDK. Okay, so like for the ESP32, it's made by a company called Espressif. There's an Espressif SDK. It's a coding language like for that specific processor. Okay, or you can use like more generic code like Arduino, C and C++, for that same purpose as well. Okay, but these controllers have specific code that you could write for them, or more general code that you could write for them in this way. Okay, so just like that, the Arduino IDE, which is one thing we're working with, remember it's the blue icon or the blue software, is not the only thing that can compile and run the Arduino language. There's another platform called Platform.io that also allows you to do it. It's kind of like more advanced. That's like a kind of a more traditional IDE. It's more like VS Code than it is kind of like than the Arduino IDE, which is more like Scratch. It's kind of like high school plus level. It's like college, high school level is the Arduino IDE, the blue one. And then Platform.io is kind of like the more professional version, like it's an actual coding environment, literally built into VS Code. It's easier to work with, like GitHub and documentation, things like that. So it can also work with Arduino. It's not, you're not locked into this software by any means. I also wanted to, kind of take a step back and realize, why are we going through the trouble of learning this? And so this is kind of my pitch, that understanding electronics is all well and good, but they really are everywhere in our modern day. And I think you do benefit by knowing about them, how they work, where they are, how they function, when they break, how to fix them if possible. This ability can make you stand out in the world, in the workplace, and just, I don't know, I like learning stuff about the world. I hope you guys would too. So it's just one of those things that you can know if you wish to do so. So I'm here to tell you all about it. Okay, and it is definitely, Arduino especially, is showing up in our professional spaces more often, because people like me who deal with it in high school, will grow up someday and then make something or use something quickly that turns into an Arduino-based project. And then a funny thing that happens in industry is that prototypes can often end up accidentally or otherwise becoming products. And then you have Arduinos, built into $1 million machines running multi-million dollar processes that, if they go down, is big bucks, and someone's got to fix it. Someone's got to know how it works and to maintain it and to add new features to it and all that good stuff. So typically, the people to know that are the younger people in the workplace. So it is definitely a value add to know how to do this stuff, or to say that you could learn how to do it if you didn't know immediately what it was, right? An Arduino, I know what that is, or that sensor, I know what that is, or how it works a little bit, and then you figure the rest out with Google or with ChatGPT, or whatever you have to do to make it work. But where you guys might be right now is kind of like at the getting started phase, and I just wanted to let you know that it is a relatively easy ease of entry. I would argue that you guys are already past the difficult part, which is looking at the IDE for the first time and kind of knowing what's going on, right? Is like reading the language on the board and seeing gibberish for the first or second time, and now you might kind of know what's going on and how to use it. And then the world kind of opens up, and it's a fairly accessible world. So this kit, for example, is probably 30, 35 bucks. For example, it's a bigger kit, it's tons of sensors in here, but you could just as easily get one for $15 or $20. That would be a really good ease of entry that would get you just past the door, just past the threshold, right? It typically doesn't need soldering. Everything's just kind of plug and play, at least with breadboarding or breadboard wires. Really great for more hands-on learning. If anything about this class, the practicality part of it appeals to you, and you want a little bit more of it, highly recommend picking up a kit. You don't have to have a name brand Arduino. If you feel like supporting the cause, it's almost like a donation, because they are open source and they do all these tutorials and things like that. Their Arduinos cost more. It's like $20 for an Arduino Uno versus $8 for the Chinese clone. But they're not really any worse anymore these days. They're essentially the same thing functionality wise. So if you feel like supporting what they do, then you're more than welcome to do that. But I won't guilt you for getting one of the cheaper ones or a multi-pack or whatever, because like I said, for $15, you can get like 3 ESP32s that all are Wi-Fi and Bluetooth, and they have like, a dozen I/O pins and analog in and out, and they can run speakers and small television sets and all that crazy stuff. So like, pretty low bar of entry, I would say, just as a general reminder. And it really is, it leads up to this stuff, right? You don't, again, necessarily gain the ability to understand from, working with one of these kits, these Lego box kits, how to deal with, like, I don't know, an X-ray machine or something that this Arduino will be running. But it gives you the foundation, right? Again, that the terms, how it all fits together, that you could be the guy for the job when it comes time to be that guy. Okay. So, time to really dig into it in terms of like what a computer is and does and works. Okay, so we've gone through a little bit of electrical engineering, or how electricity works. So I'm hoping that we can piece this together, kind of sub-component by sub-component. Okay, so the things to note is that most microcontroller, this is technically a development kit. Right? It's made for ease of use, not necessarily to be small or lightweight or anything else. It's made for humans to easily be able to plug stuff in. As a result, it's mostly, you can think of it as like most of this is a motherboard. It's life support for the actual computer that is on this board, okay? That we have, obviously, our USB port, our I/O, our power port. Thinking back to our PLC, we'll do PLC comparisons in a minute, but it also has a power port, although it's bare, it's not a nice barrel jack like this, and a USB port, right, for programming and for connecting, powering from our computer. Also on here is a crystal oscillator. Almost all electronics, I almost drew on the board. Almost all electronics, from calculators to wristwatches, have a crystal oscillator in it. It gives us the clock signal against which we measure time, and we do things, because every clock we do one instruction. It will, add two things together or shift a memory one place. This is the rate at which a computer thinks, right? It goes chunk, does a task, and chunk, does a task, and so on, at a fixed rate. Okay, so this rate is different for every computer. This is what we hear of when we hear clock frequency, right? It's all the rage in powerful desktop computing, for example. If something's 4 gigahertz versus 4.2 gigahertz, you go, wow, there's extra 0.2 gigahertz, because that is a extra 200 million instructions per minute, or per second, rather. So that is this clock rate, the clock feeding the computer. The computer in question here is right here, at least on the Arduino Uno, which is what this is. This is kind of like the OG, the go-to Arduino, the quintessential one. So this is the actual computer. It'll actually slot out like an old school computer chip. Okay, looks just like, kind of the quintessential IC again. And this is the one that the actual computer is. Okay, so all the rest of this, like I said, is just life support. It's things to power it, to keep it alive, to filter that power, to talk to the board through USB, right? That's kind of all the rest of this does, as well as to physically connect each of these silver pins, okay, to one of these. These are called headers, okay? When you can put a pin into it, it's called a female header, and when it sticks out, it's a male header, okay? And you can actually see, if you look real close, because this JPEG is actually really artifacty, that you can see each of these lines go straight into each of these pins, and that's literally what we're doing. So each of these pins we're making a physical connection to, and we wire in a breadboard wire, okay? And these analog pins, okay, these are special. These are the only pins on this board, a particular board, that can take analog values, okay? It can distinguish not only between low and high, okay, but the exact amount between low and high. Are we halfway? Or are we halfway? plus 1/1000th of the way, right? If we're a smidge above that point, okay? So unlike our pins for the PLC, where we have many inputs, we have I1 through I8. Okay, all of those are analog pins, okay? But on Arduino, that's not necessarily the case. On some Arduinos, none of them are analog pins. It's actually specific to the computer. That's another thing, is what an Arduino is can be many different kinds of computer. It's more like they support the Arduino language or are of the Arduino ecosystem. Okay, it's kind of a nebulous concept. I'm sorry that the term is so generic in this little niche of ours. This is the power rail. This is kind of like our upper left power input, right? I'm kind of missing it over here, but that was our ground points and our plus 24V. Okay, that is kind of like where we get our power for stuff. Okay, there's actually really conveniently, one of these pins puts out 3.3 volt power all the time. Okay, this is a 5 volt board, so we always power it with 5 volts or above. I'll explain that in a second. But we have a nice clean source of 3.3 volt power. Really commonly used for sensors. Okay, sensors love 3.3 volt power because it's really clean, it's very stable, and it doesn't necessarily have to be high power. Okay, it's power efficient, all that good stuff. 5 volts is probably for an Arduino Uno, usually what you'll connect to most things. Okay, you can think of this as like your power pin. Okay, that most things will take 5 volts. Servos will take 5 volts, molders will take 5 volts. A lot of sensors will take 5 volts. Okay. The V-in pin is special. The V-in pin is actually attached to this barrel jack. It's just as if we're putting power into this board. Okay, kind of interesting is that we can put up to 12 volts, technically up to 15, on this barrel jack or on this pin. Okay, so if you have a wall wart or a DC power supply with a barrel jack at the end of it, you could power this Arduino with that device and it would run and do its thing, you know, power motors, all that good stuff. Or you could put voltage on this pin. You know, again, say you had a power supply or whatever, you could supply voltage to that pin. Because this chip right here is the voltage regulator. Its whole job, it's essentially a 3-pin device, is that on one pin, it takes in noisy, unstable input voltage, okay, from a battery, from a power supply, from a wall wart, whatever, that might be way higher than 5 volts. Okay, this might be 15 volts or probably, let's say, 12 volts. Okay, way more than we need 5 volts. That's going into the device. And out of the device is a really nice, clean, stable source of 5 volts or 3.3 volt power. There's actually 2 different regulators on here, one for each voltage. Okay, they essentially drop down the voltage from our crazy, unstable high voltage and filter it and smooth it out and bump it down to just what we need, 5 volts or 3.3 volts, and then pipe it to each of the pins accordingly. The interesting part is this is called an LDO, or a linear regulator. Okay, these are also simple, extremely cheap devices. They cost like 5 cents each, 10 cents each, these ICs, okay? But the downside is they generate heat, okay? Because the difference in voltage, if we go from 12 volts down to 5 volts, that 7 volt drop is dissipated as heat. And the bigger the voltage drop, the bigger the difference in between our input voltage and our output voltage, the more heat we'll generate. It's just waste. It's inefficient, but it works. There's another device that other Arduinos use instead, or other professional products, called a DC to DC converter, also called a boost converter, also called a joule thief. Very cool devices. If you guys haven't heard of a joule thief before, there's lots of very cool YouTube videos, would recommend. Okay, essentially takes, actually this is a buck or boost, takes one voltage in DC and turns it into another voltage in DC. This is actually a very complicated thing to do. In AC electronics, all you need is a transformer. That's it, super simple, dead simple. Windings in, windings out, right, gives you that ratio. But in DC electronics, it's not so simple. We can't use a transformer for that. We have to use these complicated, weird electronics like LDOs and DC to DC buck boost converters. But at the end of the day, they just turn one power voltage into another power voltage, okay? I'll go back to that in a second, but one thing I want to talk about is for data voltages that are different. For example, sensors, right? If you have a 12 volt sensor and you try to wire that into a 5 volt Arduino, you're going to get some smelly white smoke pretty fast, okay? So how do you deal with that? You use this device called a level shifter. These are also like 50 cents each on Amazon. They come in like packs of 10. And they just shift one level to the other. You wire one general high voltage here and the other general low voltage here, and it will translate in between the two, to and from, nice and easy, bidirectional communication. Okay, so 12 volt stuff can talk to 3.3 volt stuff and vice versa, but it can't really be used to move sizable amounts of power. Okay, that's the caveat. It's really only data or information exchange. Okay, but so in the future, I'm probably going to get these, and so I'll probably get one of these Arduino sensor packs, a few of these level shifters, and then make some 12 volt sensors to use for PLCs. Or in the future, if you guys were tasked with such a thing, you wanted to avoid using an Arduino altogether, you had a sensor that talked 5 volts and you wanted to wire it into a PLC that only understood 10 or 12, you would use one of these, right? You would use one of these to bridge the gap to get it talking 10 volts, 12 volts, whatever, and then proceed accordingly, okay? All right. Most devices will have TX and RX pins, really useful. It essentially is just, are we sending bits to our chip or from our chip? Really useful for seeing, is it alive? Essentially, is it taking data? Is it sending back information? Things like that. We also have a user accessible LED. Just like our onboard PLC LED or user LED, Arduinos also have built-in LEDs, mostly for debugging, right? Am I alive? Is the process working? When we're sending a message, blinking a light, things like that. We also have just a general power LED that's always on as terms of keep alive signal. Okay, and the last thing is the programming pin. We don't have to deal with this because for like 90% of hobby stuff, you'll just be programming through USB. But this chip technically has a built-in programmer on it that it can program itself, essentially, with the USB. Okay, but we could also program it externally. That is what an ICSP pin or ICSP header is, FYI. Okay, now, dialing down a little bit more. We're not gonna get too into it, okay, but I just wanted to show you guys that even the simplest things are systems of systems, right? All this stuff is complicated. But the point of this is that despite all this complexity, it's kind of handled for us in the Arduino language or in the Arduino ecosystem, that we don't really have to deal with all this stuff, but it doesn't mean that it's not there, okay? And it's, I think, interesting to know about and what a computer actually is, or what a microcontroller or a microcomputer actually is, okay? And so what that is, what it consists of, is very often it will have another timer in it or another oscillator, one or more oscillators. So there's an external clock and an internal clock. Oftentimes external clocks are temperature compensated. So clocks will drift over time. It's why clocks will gain and lose seconds, for example, is that if this square wave is supposed to go up and down at 12 million times a second, and it goes at 12 million point 0.00001 per second, it's going to drift over time as it moves to and fro, as the temperature changes, as pressure changes. But external oscillators have temperature compensation and pressure compensation to deal with that. They're more expensive parts, but internal ones are typically more energy efficient, so they have them in there too. So what you're seeing here is kind of our cartoon of what the actual silica would look like. Okay, so this gray square here is the silica wafer. Okay, and then each of these subsections is just a component of the overall circuit network that's etched into that silicon. Okay, that each has a functional part. But there aren't really like bespoke parts, it's all just silicone. Okay, wires and connections, sometimes pieces of memory, right? Temporary and permanent. Okay, so we have timers. Timers are actually things that cycle off of the original clock. So one timer, for example, will count the number of cycles and count up every time the square wave happens. Other timers will count every other square wave. Other timers will count every other square wave. Okay, there's different sets of timers and each of them does different things. They're great for generating clocks. PWM, servo timers, all that stuff is generated with these timers. You can kind of think of them as like voice tracks, trying to make a piece of music, right? It has the track for the saxophone, the track for the drums, the track for the guitar. Each of those tracks running alongside each other is one of these timers. Okay, and they're used for things that happen simultaneously. Essentially, it allows our single core processor here to multitask. It's kind of like a co-processor that generates signals for us. Okay. We have RAM, just like a normal computer. We have temporary variables. That's whenever we create a variable in a loop, whenever we initialize an int or initialize a bool, that gets stuck in this piece of memory. Okay, random access memory. Okay, there's program memory. This is the read-only memory that gets programmed in when we program the device. So we compile and then program. When we push code to the device, this is the section of code or memory that code gets shoved into. Okay, this is where it lives. So when the device boots, the first thing that it does is it reads a bit of thing called the bootloader, and the bootloader says, start reading here, and it points to the program memory, and then it says go, and then it just starts looping within that memory. Okay, EEPROM is also a special kind of memory. It's permanent memory, but it's rewritable. It's useful for settings, for example. So when you want to change settings on a device and have it remember that after it goes to sleep and reboots again, you would write that to EEPROM. We also have I/O ports and peripherals. Peripherals are, again, it's kind of like a coprocessor. It lets us do crazy complicated things really, really fast, really, really precisely, but without taking cycles on the main CPU. It's kind of like a mini brain that says, here, do this, handle this process, and it will. Things like talking UART or serial, right? Our characters over the line get designated to that little coprocessor. When we talk SPI or I2C to our sensors, we're using this little part of our brain here, part of our processor. Okay. And that's pretty much it in a nutshell. There may also be things like temperature sensors in there. You know, if it is a particularly performance processor that can overheat or needs to underclock itself, you'll have a temperature sensor in there. As well as many other kinds of peripherals that I didn't mention. There is simpler, really low cost processors that, you know, X out half of these things. They just don't need it for the application, so it's cheaper to make it without. And there's things with 5 times as many, right? More I/O pins, more peripherals, more timers, whatever needs to sell. The interesting part of a microcontroller is that it was at one point just what we would call a computer. That really a microprocessor, you know, what we would think is a processor inside of a computer are desktop computers, and what we would consider a microcontroller were one and the same. Particularly around the 1970, 1980, kind of like really up to the 80, 86. These are those little black chips, same as on our Arduino board, right? But they were desktops. They were the computers of the time as small as we could make them and functionalize them, right? And then right around the time of like the 386, 486 Pentium, this is when we started to see kind of like the bifurcation of the super performance, high energy computing cluster processors and the really high performance, high reliability, high ruggedness, high efficiency microcontrollers that we are today. And some of them, like I said, the Arduino Uno, or the AT Mega 328P, comes in right around here. It's like 1980, 1990, okay, right before kind of that fork in the road happened. But we still use it today because it's efficient, because it's easy to learn, because it's low power. It handles just enough of our needs that we really don't need the power hungry, crazy high transistor counts that other processors are optimizing for, right? And there's even microcontrollers come out every day, or every year rather, new ones that are higher efficiency, that do more processing for less wattage, or that have like higher transmission rates or ranges or whatever. Okay, that they're still coming out. They're just kind of a different species of computer than what we would consider to be in a desktop computer, right? All right, so all of that said, it might be a bit muddy in the water, like how exactly an Arduino is different from a PLC. It's confusing. You'd be okay if you were confused by this, because you could totally make an Arduino-based setup that has the exact same elements as a PLC. You could have it, take power, 24-volt power, have a little power regulation down there to drop that down. You could install screw terminals to make it just like a PLC to have screw terminals, have relays on there where, some of your I/O pins are controlled to relays just like we have on a PLC, okay? But when it comes down to it, the software and the microcontroller that's running all of that is kind of really what is a differentiator, okay? It's the ruggedness, the reliability, the maintainability, the software that's running on there that can be the difference. Not necessarily the hardware, although PLCs often come with extremely vetted hardware, that your 1 or 2 off DIY custom board might be great, but you don't know if it'll last 5 years or 10 years, while PLCs, where they've made 1,000,002 of them, are tried and true and tested and certified or very often warranted, right? The important things in life. Another comparison is, Arduino versus Raspberry Pi, because again, there's a lot of crossover here. There can be some applications that could be just as well handled by an Arduino as by a Raspberry Pi. You would just be kind of overpaying if you put a Raspberry Pi in there, because it's like $30 difference depending on the one that you buy.
They're expensive.
Well, the latest ones are, yeah, especially during the Corona and all that. Oh yeah. In my work, we were actually buying them for like black market prices, not black market, what do you call it, scalping prices.
Oh, really?
Oh yeah, we would buy like dozens at a time for like $300 for a Raspberry Pi, because you could not get any. And we had customers, again, $1 million applications running on a Raspberry Pi, and you could not get one. What do? You pay $300 for a Raspberry Pi, that's what you do.
I was mad when I paid
No, that's not that bad, actually. Yeah, in the grand scheme of things. But yeah, that's worth noting, is that now there's 5 different tiers of Raspberry Pi, but you could get, any of the other tiers are not as performant, but you could also say that they're higher efficiency. They take less energy to run, and they cost less, so there's trade-offs there. But ultimately, the difference between a Raspberry Pi and an Arduino really is that a Raspberry Pi is a computer, okay? It's what we call a single board computer, or SBC. It's like a classification of computer, okay? It runs Linux. It can connect to displays and keyboards and mices. It is a computer, as far as we've been able to miniaturize one today and put it on a single board, hence the name, okay? But at the same time, it can do a lot of things that an Arduino can do. It has general purpose input-output pins. Okay, it can talk to sensors, it can command motors. it's only 3.3 volts, so servos will have a hard time talking to it. Most servos are 5 volts, but there's solutions for that. But a lot of sensors will plug right in. You could plug in an I2C sensor into a Raspberry Pi or an Uno. The difference might be, do you want it to connect to the internet, for example? Or are you working in a higher level programming language? Here we're pretty much stuck in an Arduino land, C and C++. But here we have a litany of different options for programming. We can do Python, we can do JavaScript, we can do Node-RED, all kinds of stuff that could even attach to those low-level pins and drive them and do what we want. But it does cost $50, for the latest one, $60, I think. 80 for the latest, 70? Okay, yeah, that sounds about right. So expensive, as opposed to like 7 or 8. So for a given application, it makes sense to go one or the other if you have the choice of both. But ultimately, they are different. Power efficiency is also much different. It is so much easier to run an Uno on a solar panel than it is to run a Raspberry Pi. Okay, like an order of magnitude of different energy consumption there. More things to think about, more differences. Okay. This is again where that level shifter conversation comes up. You'll have to look at your sensor that you're using, the motor that you're using. What we were talking about motor drivers, right? The things that talk to our motor, in between our PLC or our microcontroller. Those also have certain voltages that they expect to be talked to in. So most will support 3.3 volts, but all might not, right? They might be expecting a slightly higher voltage or a 5 volt signal there. So level shifters can help. And at the end of the day, when we're talking about, between the litany of choices that one might have if they're confronted with this problem, is what's right for your application. And it really just depends on the situation. What is your budget? Can you afford a $300 PLC or a $30 Arduino, or a Raspberry Pi? What is the cost of that system failing? Again, how much do you want to stake on that $8 machine? Or do you want to spend, the extra $300 to make sure that it's rugged and reliable and industrial grade and all that good stuff? Or do you really need the extra processing power? Are you dealing with like image processing, or do you have to talk over the internet, or is your sensor a USB device? That comes up a lot, right? Is that you would have a USB device somehow? All those are things that you have to consider when it comes to the choice of application, because let's face it, for many things, a PLC or an Arduino or a Raspberry Pi is just a computer in a box in a cabinet somewhere. And all that matters is that the outputs are driven according to the inputs in the correct fashion, and that it doesn't fail so often that it aggravates the wrong people, right? So that really is all part of the choices in terms of which one do you want to go forward with, as well as which one are you comfortable with. As I said, as long as it does the thing that you want it to do, it doesn't really matter how you get there, in my opinion. So get there how you can in the budget allotted. Time is a part of budget too, right? Any questions so far? Okay. All right, so next up we're gonna do a review. I expect or would hope that you guys kind of bookmark the next few slides, because each of them will be a rundown on each of the commands that I think are foundational to using Arduino as a language. Okay, we're gonna go over all the critical components, the critical commands, and a few examples. So it'll be a great resource to refer back to. We are gonna have a little bit of practice in Arduino, so this will be useful for that, I think. All right, so first up is pin mode. Okay, so I won't labor on this point too much. I know I brought it up a few times, but here's a great lookup for essentially the 3 different kinds of pin modes you can set up. We can do an input, we can do a pulled up input, which is a default high input, right? It's not floating when there's nothing attached to it. It is high when there's nothing attached to it. And we can set it as an output where we expect it to drive something. Okay, the general is that it takes this function, the pin mode function, takes two arguments. It takes a pin argument, which pin are we changing? In this case, we're changing the A5 pin or the analog pin. The analog pin can work with digital too. And we're changing it to a state. Okay, that state can be we're changing it to a configuration, right? So input pull-up, or output. It's three choices. All right, here we're talking about digital write. Digital write also takes two arguments. Just like before, we have the pin argument. Again, it can be 0, 1, 2, 3, 4, 5, whatever, including A0 through A5. And then the state can be high or low. I should have expounded on this in the presentation, but I also should note that in Arduino, high is literally defined, it equals 1, the number 1, okay? Just like low equals 0. You could use them interchangeably. You could also write true or false. But if I remember correctly, no, sorry, it is lowercase. In some languages, it is capitalization important, but I think it's just lowercase in Arduino. Okay, so these things also mean the same thing. You could literally say digital write 5 true, and it would be the same thing as digital write 5 high. Okay, is the point that I'm trying to make. Okay, so the outcome of changing that state, right, as we go down our loop, doing one line after another line after another line, and then we hit our digital write line. Okay, what's happening when we do that is, we're doing other things, and then we hit the command to turn the voltage high. So it spikes upwards. We see a little bit of ringing here. That's what this is called, where we have a little bit of overshoot, but it settles down to our stable 5-volt high signal, and then we turn it off. We blip it back off. This is an on-off blip. We blip back down, a little bit of ringing down here, but then we settle at 0 volts until we go back up again. So it's literally changing the voltage on that line from 0 to 5 volts. I/O pins can source a small amount of current. Fun fact. Okay, so they can give 5 volts typically for an Arduino, or 3.3 volts. But then they can also output about 10 milliamps on that pin. Okay, it's just enough power to drive an LED. It's actually why it's best practice to put a resistor on LEDs. You can drive resistors raw, but technically it kind of like takes all the power that the pin can source, which is not the best practice. 10 milliamps is fairly small, but you can use it to drive very small motors, at 10 milliamps, mostly logic outputs, which is, the name of the game here. But essentially it can source just enough electricity to affect how much voltage is on that line, high or low. And then we use that to talk to the world. Here's our example on reading things about the world, right? Is making a variable. So this is how we declare a variable. Here it could be a Boolean or an integer. Both can store the numbers 0 and 1, and that's all we need from this equation, is to store 0 or 1. So an integer, int x, or a Boolean, bool x, equals this would be just fine. Okay. The only argument, it only takes one argument, is the pin, whichever pin we're looking at, whichever pin we previously configured as an input or an input pull-up. And then here we are reading that pin. Okay, so whatever the result is, high or low, 0 or 1, true or false, that'll get stored into this X. Okay, so the next line down, if we were to print that or say, turn on the LED according to what is stored in X, and it'll look at X, see 0 or 1, and then light the LED accordingly. Okay. Here is an example of an external pull-down resistor. Okay, so just like a pull-up resistor, the pull-down resistor stabilizes our state. Okay, it means that when the button is not pushed, we know the state that we'll be reading on our pin. That state will be low instead of high. Okay, it's really the same thing. Functionally, it's having a pull-up. Having a pull-down is just the opposite state. So when the button is not pushed, we will see low, as opposed to our pull-up, where when the button was not pushed, we saw high. It was our default state. Okay. So we wouldn't have had to declare our pin, which is 5 in this case, as input pull-up because we have an external pull-down. We would just set it as input. Okay. But doing that, we can read the state on pin 2 in this case. So I should have put digital read 2 instead of digital read 5 over there, but we would be reading the state on 2. When this button is not pushed, the state on 2 is ground, right? Because we're going to ground. But when we complete the button, when we close the button, okay, we will see high, because 5 volts will come through here, and then we will see high volts on our 2, okay? Again, pardon the artifacting on this one. I know it's kind of hellish, but this was honestly the best picture I could find. Talking about analog read. Okay, again, analog being any signal from their minimum ground reference, 0 volts, to our maximum analog reference, which is usually just our input voltage, such as 5 volts. What would be a linear scale from 0 volts to 5 volts, for example, halfway on that scale would be 2.5 volts, is mapped to a value between 0 and some maximum. For example, 255 or 1024 or 4048 for 8-bit, 12-bit, I believe, or 10-bit, 12-bit. I believe so. Okay, so often this scale is chunked up into the smallest changes that we can discern from one step to the other, and then we just count those steps to get to a point. Okay, so that point, or the number of steps between 0 and the number of steps that it gets to our point, is stored in our variable when we call analog read. Okay, so if I had 2.5 volts on my A5 pin, whichever it is in this fuzzy mess, and so 2.5 volts would read as 127 on a 255 scale, right? It's half of that scale. And then so X would be stored in as 127. Then whenever you told it to print or to, compare it against some other value, you would compare X to that value, or you would scale it first, convert it back into the thing you're actually interested in and proceed from there. Okay. Okay. PWM, complicated topic. Again, really recommend you guys look up videos on this stuff if you're at all interested in learning more. Once you understand it the first time, it clicks every time after, so if you're not quite at that point, I recommend a couple more minutes to try to get there. I think you will. But at the end of the day, really the critical concept to understand is the concept of a duty cycle. Okay, this is a 0%, if this is low and this is high, duty cycle. This is a 100% duty cycle. This is a 50%. and this is a 25%. Okay, so the key to a duty cycle, to understanding a duty cycle, is to understand that this pattern repeats over and over and over again. Okay, so for a 50% duty cycle, we play this wave over and over and over again. Okay, so you can kind of think of it like a wave or a square of this thickness plays every so often, over and over and over and over. And a lesser duty cycle will have a thinner blip. Okay, it'll still occur at the same time. It'll just stay on for less time. Okay, do you guys see how this is a smaller duty cycle and we're just shifting how far apart the wave is? Okay, so this pattern actually happens like tens of thousands of times per second. Okay, tens of kilohertz that these signals happen. So when we say a PWM signal of some duty cycle, we're just talking about between 0 and 100%. But remember, we scale it differently. There's 255 different chunks of 0 to 100%. Okay, so each chunk of our 255 will be like 2.5%-ish difference. You can think of it like, right? So if we say analog write 1, that would be a duty cycle of 2.5%. If we did analog write 2, that would be 5-ish%, right? And if we did 255, that would be all the way on. And if we did 0, it would be all the way off. Okay? Yes?
What is the purpose of this? What would you use it for?
The purpose of this is to emulate an analog signal. So it's actually a really clever way that the signal, if we were to read it with a slower measuring device, or you can think of it like if we average the signal, the average voltage will be different. Okay, it might be here for a high duty cycle, and it will be here for a low duty cycle. Okay, so this average might average out to be like 2.5 volts for our 50%, but this one would average out to 1.25 volts. You see how that's 25% of 5 volts? And then we get our analog back. So if we do a blip more, 2.5%, we could maybe get to, 1.35 volts and then have that kind of granularity of control. That's what it's all about. If we change that signal fast enough, 1 millisecond we play this voltage, the next millisecond we play that voltage, we can get sound playback, where we get specific intensities of analog output going to a voltage signal. This is literally digital to analog conversion, or one way of making it. It's literally, PWM is like the poor man's digital to analog conversion. There's better methods of doing this that are higher sound fidelity, that are better at it, but it is a way of making an analog output voltage with a digital input. And that's the gist. So most Arduinos, again, the amount of level, right, the frequency, the granularity that we can control this signal is a selling point of the processor. Different ones have 8 bits, some have 10 bits or 12 bits, right? The finer tune that you can make that signal until you kind of approximate high level or highly accurate controllers, okay? We can also control outputs with this. For example, servos take PWM signals, where often servos will have a limited range, right? So you could say between, for example, 0 degrees and 270 degrees. And then this range is mapped by a PWM signal between 0 and 100% of our PWM, or 0 to 255 for our analog. So if we analog write to our servo input pin, right? Servo pins typically have a ground pin, a input pin, which is what I'm talking about here, and a power pin, 5 volts. So if we wire our Arduino, our PLC or whatever to this input pin, and we write our 50% duty cycle, our 128 analog write value, the servo will zoom to 50%. Okay? If we wrote 75%, it would zoom to 75% of rotation, same for 25%, and so on and so forth. Okay? So what the servo is literally getting is actually this weird sawtooth signal, but it knows how to decode that, where based on the width of the signal, it can know the position to go to in kind of like a lookup. And it's not the only one that can do that. There's also proportional valves that can open or close, be more opened or more closed depending on the PWM signal it gets. It's very common. Motor speed controllers have that as well. Just another way that we can interact with our world with granularity, right? Speed controllers work with that a lot. Very common. This is also, by the way, how LED dimming works. If you see a digital device that can brighten or dim an LED, it's mostly done with PWM. It's actually blinking on and off very quickly, but the amount of light that comes out of it is averaged to our eyeballs. It appears to be more bright or more dim because the total amount of photons that comes out per second changes. Fun fact, but it is actually flashing very quickly at tens of thousands of times per second. All right, we're actually flying through this presentation. I hope it's not dragging too much. We're making good time, extremely good time actually. Okay, so getting into higher level stuff here. The underlying message really is, again, refer to your examples in Arduino IDE, not necessarily in our PLC. The PLC has unfortunately few examples, but the Arduino IDE has built-in examples right in the file tab menu. It has plenty of examples on how to do I240 and SPI and all that other stuff. That's where this code came from. Okay, you don't necessarily have to remember it every time, or you could even ask ChatGPT. I'd recommend doing that. But it is essentially the same no matter what we do. Okay, and it always looks the same for I2C. If you guys hadn't seen it before, it starts with including our library. This is our library call. It brings in all of the code that is within this document. This wire.h is actually its own sketch that's like 1,000 lines long. Someone wrote like 30 years ago and enables our Arduino to talk I2C. Inside of our setup function, the one that only runs once is our begin call, where we join the bus. Again, there's lots of things that this does behind the scenes that tidies up and connects to the bus and starts communicating on it. Same with our serial bus. This is talking to our debug menu on our computer. The human readable, this is the current temperature, this is the pressure over time that we tell ourselves when we say print lines, okay? So that is that interface, and here's our loop. So what will almost always happen is that we will request information from our device. Okay, so we're requesting 6 bytes of information from peripheral device number 8. There could be up to 255 other devices all on the bus. Each one could be a temperature sensor, a pressure sensor, or whatever. Okay, and then within our loop, we have another loop. You guys actually haven't seen this before. It's called a while loop. A while loop occurs until its condition, okay, the thing within the parentheses is no longer true. Okay, so a common thing, we haven't actually encountered this before, but if you guys want to make a loop that lasts forever, like until the end of time forever, until the device turns off, whichever comes first, in that case, you can do while 1. And then the code, oh God, that's awful. And then the code that you want to do. Okay, because remember, this while will run this loop, anything inside of here, while its condition is true. 1 is always true, so it will run forever. It'll hit the end, go back here, while this is true, 1 is true, and then it'll keep on chugging. And it'll just keep doing that forever and ever. So our void loop, fun fact, again, is that behind the scenes somewhere there's something that defines what the loop function is, and it's just a while loop that, once we hit it, we're in there forever and ever more. We just keep cycling through. Sometimes, though, we want to wait for something. While no data, for example, is a very common thing. Or while we are connected to the bus still. Again, another common thing. In this case, it's while we have data available for us to read. Okay, because we had that little subsection of our brain that was just devoted to I²C. It can see when we get messages. A little flag comes up that says, hey, we have data ready and waiting. Our computer doesn't have to spend time fetching that data. We can just see, hey, there's 8 bytes waiting for you, whatever. There we go, cool, read in those 8 bytes. And then we were already expecting those, so we get our information back in the form of whatever. We could treat it as raw bytes, that those bytes might be meaningful. It might be a manufacturing name. It might be a temperature value. It might be the contents of a setting that we were trying to get from a configuration. It's whatever we requested from the device. I²C sensors aren't necessarily sensors. They can also be command devices. Motors can be commanded. Heaters can be commanded. Displays are very often I²C. You can do some pretty complicated stuff with it. And only with 4 wires. Our ground connection, our power connection, and SDA and SCL are always the pins for I²C. When you see SDA and SCL, you're dealing with a I²C sensor. All right, just a couple more things until we get a practice break. All right, so last bit about SPI is that it works very similarly to I²C, except it uses more pins, uses more wires. It doesn't share as many per device, okay? The SPI devices will almost always have a very specific library for that device. Same for I²C. So if you get a SparkFun pressure sensor or an Adafruit temperature sensor, you would look up the library for that sensor, and then it would have that in the name almost, and it would download right away, work for your device. SPI devices are just like that, and the cool thing is that when you download those libraries for your weird sensor, they will almost always come with examples, as they will amend your examples file menu to include examples just for that sensor. And it'll break it down like how to use it basically, how to use the advanced configuration, all really good stuff. So you almost always have a basis of what you're doing or how to work with whatever you want to work with. You don't need to be intimidated. As long as your connections work, the software will almost always follow. This is the last of our communication protocols. Our first few being UART and I²C, I2C, and SPI. This last one, it really comes up mostly for temperature sensors. There's a lot of these devices, they look just like this. They come at the end of a long black wire, and then they have a silver can at the end, temperature probe. They actually only use 1 wire. Remember, SPI uses MISO, MOSI, SCK, CS, power and ground, 6 wires at least, 4 for I²C. This guy just needs 3 and only 1 for data. That's its big draw. Some devices can even just get away with 2 wires, where 1 wire is ground and then the other wire is data that it parasitically draws power through. Kind of cool. But that's its claim to fame, is that it only uses 3 wires, and some called a 1-wire protocol. Also called the Dallas temperature sensors for some reason. That I don't know why, maybe that was the name of the company. But aside from a pull-up, these almost always need a pull-up resistor added to them. So if you try to use one of these in the future and don't know why it's not working, it's because you don't have a pull-up on it. They are otherwise extremely easy to use, okay? Where again, it'll have a library for it, where you can call sensor.temperature and then get back a human readable temperature in Celsius down to the 10th of a degree. Okay, they're cheap and effective. You just got to know how to work with them, how to connect them, and how to write software for them. And it's easier than you think, I think. Okay, so bringing us back into the relevant part of how the heck do we use Arduino with a PLC directly. And the good news is that there is actually an Arduino baked into our PLC. There is the main PLC processor, and that's the one that we push code to whenever we compile it within our IDE. Okay, but there's also another processor inside, a coprocessor, that's just for running Arduino code. And that we can work with today. to do logic on it. You can use it as like a math coprocessor if you want. But really the main thing that it's great for in terms of our PLC is communication. It talks Modbus, it talks Wi-Fi, it talks Bluetooth, all that good stuff. But otherwise it really is just a coprocessor to do whatever you want. It can share variables, it can control relays, it can read inputs to help out your main programs, you know, kind of more advanced functionality for your simpler, reliable stuff. Okay, the way that we access it, if you guys want to dig into your computers and launch the IDE, I can point it out to you. But when you make a new program, in your resources tab, you know, normally where we put our programmable inputs and relay outputs and all that good stuff, if you double click on Sketch, so double click on Sketch, it will open a window that looks remarkably like the Windows IDE. Okay. So at this point, based on our previous lab, okay, we've done a little bit of Arduino already, programming in the simulator. I'd like you guys to test relay outputs using Arduino. I'm going to walk you through it at first, but then I want you guys to have some practice writing Arduino code within the PLC IDE. Okay? So I'm going to get my laptop out, but for now, yeah, I want you all to just open up the sketch and then hit compile. Okay, it's going to take a while with the Arduino sketch open, like 3 or 5 minutes.
We need one of our PLCs.
Yes.
Yes, we do.
there any specific you want us to do while doing this?
I'm just about to explain.
Okay.
Yeah, sorry for the delay.
Bless you.
All right, I'm just going to get started. There's still one thing that I have to nail down. I had it in an example at home, but I didn't make it into here. This is the bones of working with an Arduino Sketch. So once you open up the Sketch, this is essentially a standalone program that is now in the works. So whatever we run in here will run, and it'll run as fast as it possibly can. Okay, it's not like a PLC program where it runs like every 10 milliseconds or whenever we schedule it to. It'll just run and run and run and run and run, kind of like a typical Arduino runs. It'll run as fast as the little thing can, at 16 megahertz, at 60 megahertz, whatever. Okay. The different thing is that there is a little bit of a handover. There's a shared access between the PLC side of things and the Arduino side of things, right? There's information exchange, there's handoff. The two processors have to talk to each other and sync up at some point in time. Okay, so that handoff, or what variables are exchanged or what data is exchanged, is handled in the shared inputs and shared outputs category. Okay, where theoretically by changing the data or the variables in here and creating a simple ladder logic, for example, program that pays attention to those variables and changes outputs accordingly. For example, looks at a single bool that we make, and we have an Arduino program that changes that bool to be 1 or 0. And then on the PLC side, we have a dedicated ladder logic program that just has that input tied to that output that says if it's high, if it's set to 1, then our relay turns on and it's, you know, set to high. And if it's set to 0, then our relay turns off because it's set to low. Okay. But the benefit being that we can also handle networking here. We can exchange information through Modbus, right, and stick it into places or act on that information. We can get or post information from over the internet if we're talking to a server, or if we ourselves, or if the PLC is acting as a sensor and it's, you know, giving information off site. That could be done over Ethernet or through Wi-Fi. That is also something that could be done here. And there's documentation for doing so online. This is by no means an exhaustive lecture on this subject. Okay, doing Wi-Fi and BLE and all the rest of that. That's probably going to be at least in an upcoming lecture when we touch on that. But just know it is an option. It's a tutorial away, this stuff. It's an article away, talking to the internet and connecting to Wi-Fi and reading and posting data, all that stuff. The IoT basics. It could be its own class, but it's also its own YouTube video. Okay. But you could also use it for math, if there's like higher level functions, or if there's a particular library that you wanted to bundle in. You can also add Arduino libraries here as well. Okay, so if you had, you know, like a math heavy one, or one that did like data analysis or filtering or something like that, or handled a specific sensor, if you had output capabilities on your PLC, you could stick that in here and do all your typical Arduino stuff. Okay. So here comes a little bit of practice. I want you guys to write in Arduino, okay, within the PLC IDE. I want you to use the arduino.com documentation. Okay, there is actually a good amount of information on the Arduino Opta PLC tutorial. Okay, on the Arduino docs website. Okay, they have a whole tab for tutorials of interesting things. Some use Arduino, some don't. But I want you guys to do a little bit of unstructured learning, okay? Look up articles, look up videos, try simple loops, you know, for loops, while loops. Try to get variables changeover working. Try to activate relays. You know, whether a variable in Arduino turns on and off, turn the relay on and off. Okay, all this we're going to try, and then we're going to move on to function block diagrams. So we're going to have plenty of time.